Hi, good morning, good afternoon, whenever you're watching this. My name's Nathan Thain. I'm in ECSE 486 Quantum Computers class, and I wanted to take about 5 minutes today to try to explain to you Shor's algorithm, the abridged version. So we're going to go over as much detail as we can in 5 minutes. We're going to go over the basics of the algorithm, how it works, and the importance of quantum mechanics and quantum computing in solving this problem. So essentially, Peter Shor has written a paper back in the 90s to rapidly find the factors of a large number. He came up with a method using quantum mechanics to do this. So the reason that this is so important for quantum mechanics is essentially the computer science problem P equals NP. So some algorithms are in polynomial time and some are not. And the ones that aren't in polynomial time, for a sufficiently large input, we can't calculate what we want before the heat death of the universe, which is something that Peter Shor is trying to solve using quantum mechanics. So with quantum mechanics, assuming that this could be implemented into a physical system, then we could do this in polynomial time, meaning that it would be something finite much quicker that we would be able to crack very quickly. So in order to do this, we're going to start off by looking at a big number n, and we want to find the factors of n so that we can use those factors to break the encryption. And most encryptions nowadays use a large number, and factors of that large number are sort of the keys of the encryption, because it is much harder to find factors from a large number versus if you want to make a large number out of two factors, all you need to do is multiply them. So we start off step one, we make a guess G. Is G one of the factors? Probably not, because these numbers all have hundreds and hundreds of digits in them. Very unlikely. But the good news is we can use this here equation, and that's likely to give us a factor of n in either one of these two numbers. So you'll see here you got two things in parentheses here, so that's thing 1 times thing 2 is some multiple of n. That's what we're looking for to find factors of n. But how do we get this p here, this little p exponent in the g? That's what we need Shor's algorithm for. And just really quick, thanks to older algorithm from Euclid, we can find the greatest common denominator of two numbers, and that will allow us to take things that are integer multiples of the factors we want, and those to us will have essentially the same value as those factors. They'll be just as useful. So we can't really do this on classical computers, because assuming that p is even and that you don't have multiples of n in your g terms, then it would still take super long to find p. But thanks to quantum mechanics, you can take a look here in figure 1, we can run these algorithms on multiple entries at once through a superposition. And this isn't super useful to us at first, because we can only measure one value out of the superposition at a time, and most of the time this is just going to end up being white noise pretty much. But as long as we carefully collapse the superposition in a way that gets rid of the stuff we don't want and keeps the stuff that we do, then we're going to be looking good. So to find p with quantum mechanics, we start by setting up a quantum function to take input x to the gth power. Then we run that through another quantum function to find out how much larger than mn it is. So this is going to lead to a quantum state with x comma r, where r is the remainder. So let's scroll up here. And the important step here is we need to partially collapse the superposition to leave behind the terms that are useful to us. Now, what are those terms? They're going to be terms that all have some r in the remainder. And the beautiful thing is it doesn't matter what r is, because we know that p has a repeating property. G to the x and the g to the x plus p, all that, they're all going to have the same remainder. So if we find here in figure 3 all of the entries that have a certain remainder by randomly measuring our current superposition, that's going to output a bunch of things that have a distance p in between the leading terms. But we can't really measure that, since we can't read the superposition. We can only read one value at once. So this isn't still very useful to us, but the trick here is when you have multiple things that have, a period, or, if you want to get fancy with it, you call that a frequency. If you want to convert a bunch of terms that have a common frequency into just one term, one really good way to do that is the Fourier transform, and there is a quantum version of that. So we're not going to get into the quantum Fourier transform because we got 5 minutes, but we plug it in there and we get out a superposition of multiples of 1 over p. That is our frequency we're looking for, 1 over p. And essentially we can just measure this a bunch and come up with a least common multiple, and that's going to be our 1 over p. Get out of the quantum realm, invert that into p, plug it in, check it. If it doesn't work, run it again. Super quick. You can run it as much as you want. And we have found factors of n. We've broken the encryption. Congratulations. Now, just really quick, the quantum process is 4 steps. We start off by taking this initial superposition with a guess g. We raise stuff to the power of that superposition, so g to the x. Convert that into the remainder, as we said before. We collapse that superposition all into one remainder so that we have a difference in the leading terms of p, and then we run that through the quantum Fourier transform and find the least common multiple of the measured values to get p. So really quick, the figures from this presentation have come from the Minute Physics YouTube channel. Excellent YouTube channel. And they've made a very good video describing this and breaking the math down in a way that's much more accessible than Peter Shor's paper was. Bless his heart, but that man is a PhD level higher than that, I'm sure, quantum physicist, and it's very difficult to read some of these figures and equations on his paper. So having this broken down is very good. And in order to add some value on top of both of these items, just combining them in a way that's more accessible to this class, I wanted to touch on the importance of using the quantum superposition to solve this problem. So outside of the fact that a quantum superposition can run multiple calculations at once, that's not useful to us unless we get the measurement we want. Otherwise, it's still just white noise. So a superposition with multiple parts, we can partially get that to happen by collapsing out terms we don't want, by measuring terms that we end up wanting, such as the remainder from figure 3. And that will partially collapse the superposition rather, and that lets us continue with our algorithm. And then also, this isn't really something we touched on in class, but with multiple measurements of a superposition, you could use that to find like a long-term average of a measurement, and then you know roughly what that initial superposition is based on sort of a Monte Carlo simulation coming out. Or you could take a least common multiple of many such observations to find what is the actual term that you want to find, and that's what we did here. So instead of a Monte Carlo simulation, we did an LCM, which isn't something we talked about in class, but is equally valid and important way of solving a quantum, or not solving a quantum equation, rather finding the quantum, finding the state you want. So thank you so much for listening. Please let me know on Canvas in person if you have any questions. I appreciate you listening. Thank you so much, and I hope you have a great rest of your day.